at this variable elimination in more detail now. In particular, I'm going to specify the order in which we integrate out variables in a non-random way that makes sense, and why it makes sense we will understand later. So I'm writing the probability, the marginal probability of L as, and now I need space for 11 summation signs. Okay. And I will so this is step number, or variable elimination step number. I decide to first integrate out A. So we have a summation over A. And what depends on A was the probability of F given A and B times the probability of A itself. So all of that together will give me a new function or a new factor, which I'm going to call tau. And that is now a function of B and F, because A has been integrated out. And I can also, so this is the new factor. And I can also note down which factors are used at all. So the factors used in the first step are a factor that depends just on A. This was P of A. And then a factor that depends on A, B, and F. And finally, I can summarize all the variables that are involved. Which are A, B, and F. Okay, you can already tell now that this is going to be lengthy, but I believe in the value of doing this explicitly, because it will help us in constructing the junction tree later on. And those numbers here, the probability of L equals, so I have, this is a single equation here with all these summations, but we don't really need the pluses. But I've put the numbers here to count the steps. So this is variable elimination step number 1, 2, 3, 4, 5, and so on. Okay. So in the next step, I'm going to integrate out E. And what depends on E? There's, on the one hand, I, which depends on B and E. And on the other hand, there is E itself. And so the factors used here are phi of E and phi of BEI. And if I now integrate these out, I obtain a new factor tau which no longer depends on E. So only on I and B. Next I integrate out D. Collecting the terms which depend on D, I have H, the conditional of H given C and D, and the probability of D itself. Factors used are phi of D and phi of CDH. Those are also the variables involved. And after integrating out, I generate a new factor which no longer depends on D. So a factor with scope C and H. So what depends on F? We have on the one hand J, depending on F and G. But note that this factor here, the one that we created before, also depends on F. So this time we use this factor FGJ. And we use the new factor that was created down here, which depends on B and F. And the variables involved are B, F, G, and J. So, I have pushed in, if you remember the equation that we had before the break, we had all these probabilities jointly, and I've now pushed in the summations to a varying extent. The one that I've pushed in most was the summation over A. This is why I started at the bottom, and we're now working our way to the top. But these summations are still nested. Okay, so it's a single equation that comprises all these summations. And this one here is a more interesting candidate than the previous ones, because this really depends on something that was down here. So this so I could have reorganized, I could have rewritten the summations and written the summation over F just here before the summation over A. Then next I sum over G. I collect the terms depending on G, which are the probability of G as a function of B and C. And it also depends on the new factor that I have just created, namely a factor depending on B, G, and J. So why does this factor depend on B, G, and J? Because the variables involved were B, F, G, and J, and I've summed out F, and what remains is B, G, and J. Okay, and so since this depends on g, it's also implicitly dependent on this summation here. So I have the native factor g, which depends on b, c, and g, and I also have the dependence on this new factor b, g, and j. And the variables involved altogether are b, c, g, and j. Now integrating our g gives me a new factor which will depend on b, c, and j only. Okay. Next we have the summation over I. Which appears in the conditional probability of I depending on b and e. So we have this native factor BEI. But since we sum over I, we also need to include here this new factor tau depending on b and I. The variables involved are altogether b, h, I, and k. Is that true? Yeah.
Question. When we summed over f, we didn't include this native p of f depending on a and b. And now when we sum over I, why do we include this native I depending on b and e, even though it's included in this tau we also need? In the case of f, we just had this native.
Yeah, I've made a mistake anyways. Let's see if this... so there was a summation over... sorry, this term we already used. It was down here. The only term that we don't have yet is k depending on h and I. Okay, because I'm not allowed to use the same term twice, and I think this was your question already. Thanks. Somebody who follows. Great. So there must be another mistake here. This is BEI. So this should be a function of h, I, and k. Yeah, that is correct. And we get an overall dependence on b, h, I, and k. Good. Next, there's a summation over c. So we're looking for the terms involving c that do not appear elsewhere. So there is the prior probability of c. But the other terms involving c, so g given c and b and h given c and d, we have already included them, so we don't need them here. So we have the native factor phi of c, and then the new factors depending on c and h, and the new factor depending on b, c, and j. And variables involved altogether are b, c, j, and h. Then there's a summation over h. And all the terms depending on h, we have them already. So we get only dependence on the new factors BHK and BHJ. variables involved are B, H, J, and K. And we're nearing the end here. There is the summation over B. We have not included P of B anywhere yet. So we have a native factor depending on B. And then a lot of other ones. Tau of B, J, and K. That one is used here. And then we have the final summations over K and J. So for K, we still have a term not accounted for yet. Which gives us a new factor factors used are LJK and then tau JK. And here at the end we have well, if you so wish, we have a new factor that only depends on L, which was the aim of the whole procedure, to have something that is only a function of L. And it uses this new factor, JL. And variables involved are J and L. Okay, so written on the left-hand side is this factorization of the joint that we had before. And which unfortunately is no longer on the blackboard. I will repeat it here. You don't need to do it because you still have it in your notes. So this was what I had written down before the break. So up here is simply the marginal of P of L, where I've used the conditional independencies as incorporated by this graph. And this same thing has now been rewritten here on the left-hand side, simply by pushing in these summations to varying extent and by rearranging the terms. Oh, and I've forgotten here the prior probabilities, P of E, P of D. Okay. So for instance, we brought in the summation over A to the very end, and also included, of course, this factor here because it also depended on A. And that is the last line of what's written here. And then secondly, we pushed in the summation over E, collecting all the terms that depended on E on the way, and so on. Now there is actually a nicer way of putting, I could use parentheses here, because, for example, this summation over E here does not involve A. So I could parentheses around and thus further simplify the calculation. And we will do so in a later step. So what has happened? We have computed a new factor by taking a sum and by evaluating a product. And this taken together has become a message, or we can interpret this as a message. And this message was used elsewhere in the calculation, where again we've taken, so this message, for instance, was used here, where again we've taken a sum and a product of this factor here with the new message. So all of these taus can be seen as messages. And that in turn gave a new message which was passed on. So already at this point you can see that in some way what we're doing is passing messages. Now the cost of this variable elimination, the one that I've used here, is a particularly good sequence of numbers. And if you had, for instance, simply summed out first A and then B and then C and so on, you would have come up with more variables involved somewhere in the middle. And that matters because the cost of variable elimination is dominated or is governed by the size of the generated intermediate factors. And so the true implication of the statement you will see in particular if you use a bad series of variable or a bad sequence of variables to be eliminated. Why this statement? Because really what you do when you sum out is you work with as many variables involved as is written here. So for this particular sequence of variables to be eliminated, we only have to work with tables comprising 4 indices. But if you take a bad order, then you work with even higher dimensional tables, which is more costly. So to find a good sequence of variables to be eliminated, one can study a graph that reflects the size of these factors. So you can construct an undirected graph that has a fully connected subgraph. And such fully connected subgraphs are also called cliques. Over the scope of each factor. And that in turn allows the definition of an induced graph which is the union of all undirected graphs that result from different steps of the variable elimination. And in this induced graph, two variables in this induced graph are connected by an edge if they both appear, if both these corresponding variables appear in one of the intermediate factors that were generated in the variable elimination. So these two nodes in the induced graph are connected by an edge if they both appear in some of the intermediate factors that were generated by variable elimination. So in other words, you want these induced graphs to have as small cliques or as small a width as possible. And by the way, every induced graph is chordal, meaning that the minimal loops are of length 3. So let me show that in an example. So shown here is our graph, which has been moralized. So really what we're looking at is this graph of the undirected edges, except that those edges that were originally directed, they have still retained the arrows, but you can ignore the arrowheads. So note these new connections here. So for example, we have this factor P of L. We have this factor P of L given J and K. So in other words, a factor of J, K, and L. And in this induced graph, we want a clique or a fully connected subgraph for each of these factors. So j, k, and l are in one factor, so we should have a fully connected subgraph, and this is why this edge has been added. And for the same reason, you see edges have been added in other places. And we can now use the exact sequence of variable eliminations that I have used. And in this tool, by the way, so you see the factors that are currently in the graph. And if I now sum out A, I have eliminated the factor depending on A and the factor depending, or sorry, you don't see all of that. So I have eliminated the factor depending on A and the factor depending on A of B. But I have introduced a new factor depending on F on F. So this, we had written this as tau of B and F in the last row of the table. And okay, we can do that for a few steps until, so there's something interesting happening here. Namely, I now will sum out F, and this creates a new factor depending on B, G, and J. And because B, G, and J are not fully connected yet, there will be a new edge appearing here. So you see there's this new factor, G, J, and B. And because it is a factor, I must have a fully connected subgraph here. I must have a clique in this graph. Okay, and I can go on and on with the rest. And you see that this is now the induced graph. So what's shown here is an edge between two nodes if these two variables ever appear together in a factor somewhere along the elimination strategy. And so if your computer has limited RAM, then the difficult step are those factors or those cliques comprising lots of members. So this was a good strategy. Let's look at a bad one. Let's say I will simply do eliminate the variables in the order, D and E, in alphabetical order. And you see that now the induced graph has a lot more edges. And if you look at the factors that were eliminated, there was, for instance, here a factor depending on 6 variables, on F, G, I, H, E, and D. And the probability table, the corresponding one, is shown here. So you see we work with a 6-dimensional array. So this is a big table. Whereas if we use the optimum strategy or a heuristic approximation of the optimum strategy, the biggest, sorry, I need to reset this. The biggest table that I had involved anywhere comprised just 3 variables. So we can look at any of these. You see it's a much smaller table. So variable elimination is a general strategy, but its cost really strongly depends on whether you have a good or a bad sequence of eliminations. Now, unfortunately, finding the optimum sequence is NP hard. However, no need to become depressed. As often with NP hard problems, there are good heuristics, and that's also the case here. So variable elimination for the kind of graphs we're looking at here always works. But the cost strongly depends on the sequence that you pick and finding the best elimination sequence is NP hard. And the proof of this is, for instance, in this proof by Koller. And this is why one resorts to heuristics. For instance, there is the min neighbors heuristic. Which iteratively picks that vertex in the current undirected graph which has the smallest number of neighbors. Or recommended in general is the min-fill strategy. And that's the one I had used both in the demo and in creating this table. Where you find that node next that minimizes the number of edges that need to be added to the induced graph after eliminating a node. So at a given step, during your variable elimination, you try out all the remaining variables and see what happens if I did sum this variable out. What would be the new factor generated, and would I need to add any edges to the induced graph? And let's again look at that example. So if I sum out A, how many edges will I need to add to the induced graph? None at all, because if I sum out A, I obtain a new factor depending on F and B, and we already have an edge between F and B. And next I can sum out E also without creating any new edges, and then I can sum out D still, I think, without creating new edges. And then at this point I need to create one new edge. At that point I need to create one new edge. And now I've created, I think, two new edges. So we've created a new factor H, K, and B. And we had to create two new edges because, well, you know, I want an edge between all of them, and these two were not previously available. And then, okay, so we've added very few, we've had to add very few edges to the induced graph overall. So these different strategies, they've been, all of these are heuristics, and there are others. They've been benchmarked against each other on a large number of graphs, and it turns out on average that min-fill, it's not always the best, but I think this is the one that in most of the cases perform best. Okay, now we can generalize this to an algorithm. This is the sum product variable elimination algorithm. You remember sum product? Because we iteratively always take a product and then sum over it. And then we take a new product and sum over it, and so on. This one is from the Koller and Friedman book, section 931. So as input, we have a set of factors phi and a set of variables z that should be eliminated. And we have some ordering. On this z of variables that should be eliminated. For instance, this ordering will be given by the min-fill heuristic. And we produce the following output. That is a factor depending only on y, where y is the set of all variables x minus the set of variables that are to be eliminated. So x is all variables, z are the ones that should be eliminated, and y are the remaining ones. So this formula here is a shortcut for the formula up there. We have a summation over all the variables that should be that we want to eliminate, and then we have a product of all these factors that are in the graphical model. And now comes the algorithm that shows how to find that in a smart way. So we have a variable that goes from 1 through k, where k is the number of variables that we want to eliminate. And we do the following. We compute the set of all factors that involve one of the variables that should be eliminated. So scope of phi simply says which variables does this specific factor depend on. And here we have hence collected the set of all factors that involve the variable zi that we want to eliminate. Then we have the complement. So the set of all variables or of all factors that do not involve zi. And then we have a new or an updated set of factors which consists of the old factors that were not affected in any way, and the union of that with now comes the sum product contribution. So the sum over the variable zi multiplied with the product of all factors that somehow involve zi. So altogether, this was what we had previously called tau. This is a new factor in which zi has been integrated out or has been eliminated. So altogether, this is the new or the updated set of factors. And we do this, this loop goes over all variables that should be eliminated, and at the end, so there should be another line. After the end, we construct what should be returned, namely the output factor. And the output factor is a product over all of the factors in this updated set. And this output factor can depend on more than one variable, if not all variables have been integrated out. Okay, now this is nothing new. It's just a summary of what we have already done anyways. Now if you compare. So we had some ordering. In this case, the ordering was that we sum out first A, then E, then D, then F, and so on. We had some ordering, so we had the set of factors. This was the set that I had written in the first line. And we then looped over these variables that were to be eliminated, and then collected all the factors that involve the variable to be eliminated. From that, we computed, by integrating that variable out, a new message, and stored that as a new factor. And the summation, and these new messages or new factors were obtained by always having a sum and a product of the respective terms. So that sum and that product here. Okay, so messages, or the passing of messages, has already entered implicitly, and we will make that explicit after the break, where I will also construct the junction tree that corresponds to this particular variable elimination, and I will tell you why the junction tree can be used to huge advantage when you want to do, or when you make several queries to a graph. So one way to reduce the effort has been that we have pulled in these summations, and we were able to deal with relatively low dimensional entities here. And another way we can make savings is if we are now not only interested in the posterior of L, but in the posterior of other variables also, then we don't need to do repeated variable eliminations for each of those queries, but we can reuse the results in the way that dynamic programming does. And the junction tree, which we'll see after the break, is a way to conveniently store these results that you then need in this dynamic programming approach.